Hey there, welcome to part 3 of the section 4.2 video, and this will be actually the last part. I'm sure maybe you guys are glad about that, maybe, or maybe you just enjoy watching these videos, who knows. So we're going to pick up from page 5, because last time I finished example 4 on page 4, where we had to find where f of x equals x times root 9 minus x is increasing and decreasing. So we found those intervals by taking the derivative, and seeing where the derivative is positive or negative, and it helps to be able to combine the fractions so that you can easily figure out where the derivative is 0 undefined, and then test the intervals in between those numbers, outside of them, and we find where it's increasing and decreasing. So let's talk about the mean value theorem, corollary 2 and corollary 3. Something that we hopefully should recognize by now is that if your derivative equals 0, then we expect our function to be a constant. For example, if f of x were 5, we would know that f prime x equals 0, because f of x equals 5 is just a horizontal line. The derivative is the slope of the tangent line, slope of a horizontal line scores 0, so we know that. So if your derivative equals 0 at each point of an interval I, then there's a constant c for which f of x equals c for all of your x values in that interval. Another thing to take note, and this is what we're going to kind of work with for the rest of the lesson here. Let's say you have two derivative functions that equal each other. And they're the same at each point in some interval. But here's what's going to happen. F of x is going to equal g of x plus c for all c in your interval. It does seem kind of weird, so work with me here. Let me give you a good example first, off to the side. Let's say f prime x equals 4, and g prime x also equals 4. F of x could be 4x. G of x could be 4x plus a number. What would g prime x be? It'd be 4. What would f prime x be? 4. If you were given these two functions, right? And actually, any constant. I could have put plus 5, or I could have put a constant x f of x if I wanted to. I could have done plus 10, plus 4.3. And so we kind of see why that would have to make sense. That if you have the derivative and two derivative functions equal each other, then the original function will equal the other original function plus a constant. And of course, you can move the constants around, so it doesn't really matter. So let's actually prove it really quick here. So h of x equals f of x minus g of x. If I take derivative of both sides, we know this to be true. We've seen this many times. Now let f prime x equal g prime x. If that is true, then f prime x minus g prime x equals 0. So therefore, h prime x equals 0. Well, if that's true, according to what we saw for mean value theorem corollary 2, h of x would have to equal the constant. So therefore, and I'm not sure if I've done this enough, but when you see like 3 dots like that, that means therefore. It's kind of a mathematical term. Therefore, f of x minus g of x would have to equal c, because h of x equals f of x minus g of x, or f of x equals g of x plus c. So this proof was pretty easy. And definitely corollary theory is a big deal. This actually will kind of set the tone for the second semester when we get to chapter 5. And I'll explain the term we're going to use for this process in just a couple minutes. But let's say we have all these possible, or let's say we have all these derivative functions. F prime x equals 7, f prime x equals x cubed, f prime x equals cosecant squared x, and f prime x equals 1 over x minus 3, given that x is greater than 3. Let's find all possible functions of the given derivative. So for a, if f prime x equals 7, we probably expect f of x to be 7x, right? Plus a constant, because there could be something added to it, and when I take derivative, it'll give me back to 7. Or let's look at b. If f prime x equals x cubed, Now, we noticed how when we had part A, 7x, that's 7x to the 1 power, and the derivative is 7, or it's like 7x to the 0 power. What we're doing is that we're going the opposite direction from the derivative to original function, where before, when we did the power rule, we had the original function, took the derivative by doing the power rule and dropping the exponent by 1. What if I increase the exponent by 1? Make it x to the 4 power. But if f of x is x to the 4 power, the derivative would be 4x cubed. So I'm going to put a 1/4 here. So if I did take a derivative of that, I would get x cubed. But of course, plus c. That would find all possible functions that would have that derivative. So don't forget about the plus c. Or if I look at c, now what original function we take derivative gets us cosecant squared? Hopefully you remember cotangent. The derivative cotangent is negative cosecant squared x. So we have to put a negative cotangent there, plus c. So you want to know your derivative functions. So we're just going in the opposite direction. Of what we did in sections 3.3 to 3.9. And there's a term that makes a lot of sense that we'll talk about in just a second. Or D, this is a bit sneaky. There'll be natural log of x minus 3, given that x has to be greater than 3. Because the derivative of natural log is 1 over the expression. And since we have 1 over x minus 3, the original, as a derivative, the original function is ln x minus 3. And we have to say given that x is greater than 3 because you can't natural log negative numbers. So it's very important you state that. Oh, plus c. Forgot about that as well. So this process is called anti-differentiation. So we're doing the opposite of differentiation, where we have the derivative, we want to get back to the original function. And the way you can check, do check your work, is to take your original function, take the derivative, and see if it gets back to what was given to you when you were given the derivative function. So this right here, 1/4 x4, 1/4 x4 plus 2, 1/4 x4 minus 3, they're all anti-derivatives of x cubed. So let's do a couple examples and we can wrap this up. So find the function f of x if your derivative function is 1 over 3 x to 2/3 power. And the graph of f of x passes through that point. So f prime x, if I rewrite it, would actually be this. So f of x, if I add 1 to the exponent, I get 1/3. And if I take the derivative of x to the 1/3, it's 1/3 times x to the negative 2/3. But don't forget about the plus c. Now, this one helps us find c. Because if I plug in 8 for x, so f of 8 equals 8 to the 1/3 power plus c, and of course f of 8 is negative 1, c is going to equal negative 3. So our function is going to be x to the 1/3 minus 3. And that would satisfy all the conditions set forth in the problem. Lastly, example 7. Now remember, we'll call this v of t. We'll call this s of t, right? Now remember that velocity is the derivative of position, and acceleration is the derivative of velocity, right? So s prime t equals v of t, v prime t equals a of t. And they give us the acceleration. They tell us it's 12 meters per second squared. So a of t is a constant, which is 12. So v prime t, of course, equals 12 because v prime t is a of t. So v of t is just going to be 12t plus a constant. Now they told that at 2 seconds, the velocity is 4 meters. So that means that v of 2 equals 4. So if v of 2 equals 4, we could solve for the constant. Oops, sorry, I meant to put 2 in there. So 4 equals 24 plus c. C is negative 20. So my velocity function is 12t minus 20. And then if I just kind of continue in the same manner, so s prime t is the same thing as the velocity function. So s of t, now you gotta be careful because we have 12t and you're taking the antiderivative, so we want to add 1 to the exponent. And here's what you could do. You could divide the coefficient 12 by 2 because our new exponent's 2, and that would be 6. See how 6t squared derivative 6t squared is 12t? So it's kind of doing the opposite. So we have f prime x equals a times x to the n power. Then your original function will be x to the n plus 1 a divided by n plus 1, and of course times plus a constant. Because if you took the derivative of this, it would get us this. And remember, a and n are constants here. Minus 20t, because the derivative of negative 20t is negative 20, and of course plus c. And then we're told that the initial position is negative 11, so s0 equals negative 11. So 6 times 0 squared minus 20 times 0 plus c, negative 11 equals c. So our function is s of t equals 6t squared minus 20t minus 11. And that, I think, hold on, I think I did that right. Yeah, for some reason I had a different number in my written notes, but I made a mistake in my handwritten notes. Yeah, so that pretty much concludes the video. So I wish everyone a happy Thanksgiving. I'm guessing maybe you probably watched the video after Thanksgiving, but you could see that, well, today is, you just gotta trust me, is November 26th. So my prediction for the game tomorrow, 49ers 20, and the Sea Chickens 17. Birds usually don't do well on Thanksgiving. So happy Thanksgiving, everyone. Have a great break. Oh, and lastly, SHP prediction. We'll go SHP. Los Gatos is a good team. We'll say 24 and Los Gatos 21. We win on a last second field goal. That's my prediction right there. And maybe we'll play Bellarmine or Valley Christian. We'll see. All right. Have a great break.